we're really happy to have Chloe here today. She graduated and got a PhD in 2020 for the University of Brussels. And then she immediately got a 5-year FRIB theory fellowship. And so she's affiliated with MSU and FRIB, but she's stationed at Livermore National Laboratory. Her research expertise to provide accurate theoretical description of nuclear reactions.
Yeah. Thanks. So today I'm going to talk about a reaction involving light nuclei. So I'll find a deuterium fusing to form a lithium-6, and I'm going to explain how we actually predict accurately this reaction using ab initio methods. So the work I'm going to present today is done in collaboration with people at Livermore, so Costas Cavares and Sofia Guaglioni, Guillaume Lupin from Orsay in France, and Fatna Hati in Triumph. So nuclei, so there is something wrong in my screen, I just have to, yeah. So nuclei are all around us in our everyday life. I'm pretty sure that all of you have your smartphone in your pocket or backpack, and if you were to open it, the chances are that the battery of your smartphone is made of lithium ions. So lithium elements have two stable nuclei, lithium-6, so two stable isotopes, lithium-6 and lithium-7. Here we focus on lithium-6. It has 3 protons and 3 neutrons. And the simple way of thinking about this nucleus is to see it as a fairly compact object with nucleons piling up in well-defined orbitals. So in this case, you will have 2 neutrons in the S wave and 1 in the P wave, the P3 half, and 2 protons in the S wave, S1 half, and 1 in the P3 half. If you were to bring a lot of energy, not that much actually, some energy to this lithium-6 nucleus, it will decay into an alpha particle, so composed of 2 protons and 2 neutrons, and a deuterium composed of 1 proton and 1 neutron. So something that nuclear physicists are interested about is where this lithium-6 comes from. So how this element is on Earth, and why is it surrounding us, and why we can use it in our body. So lithium-6 and other light nuclei were actually present since the beginning of time. So they were formed at the very beginning of the universe during the first few minutes. With time, the formation of heavier elements, galaxies and planets appear, but lithium-6 is really one of these elements that have been there almost forever, if you can use this word like this. So at the beginning of time, you had all this light system. So we started with a neutron and a proton that fused together to form a deuterium. This deuterium could capture a proton to make an helium tree, or a neutron to make a triton. This helium tree can itself capture a neutron to make an alpha particle, and this alpha particle can fuse with a deuterium to make a lithium-6. And at the beginning of time, you can see that the nuclei involved are pretty low masses. The largest masses that you will have will be beryllium-7 and lithium-7. So the way we describe this reaction network is using the Big Bang nucleosynthesis theory. And this theory works very well to predict the abundances of all these elements at the beginning of time, except for lithium isotopes. So there is something that we don't understand very well, is that this theory works well for all the elements represented here, but for lithium-6 and lithium-7 isotopes. On the right here, you can see the situation for these lithium isotopes. So I'm going to guide you to this plot. Here you have the baryon to photon ratio, which is given by high energy physics. We have the value measured here, measured by the Wilkinson microwave detector, which is in space. We have the Big Bang nucleosynthesis prediction for lithium-7 in blue, the Big Bang nucleosynthesis prediction for lithium-6 in red. So the prediction is the abundances in this case. And you have here what I call astrophysical measurements. So basically, I realize that you cannot see that much this line here. Basically, these are the measurements on very low metallicity stars, which are supposed to contain the abundances of these nuclei at the beginning of time. So if you look, for example, for lithium-7, the prediction would be that the abundances should be here, while the measurements are actually lower. So there is a discrepancy here. And for lithium-6, the situation is even worse because the abundances is supposed to be here, while what is observed in star is over here. So you have really several order of magnitude differences here. So there are many reasons that can explain this lithium problem, let's say. There are many hypotheses. I'm going to cite the three main ones here. The first one is that there is a problem with the high energy physics part of this calculation. So there is an inaccurate baryon to photon ratio. So if it was the case, for example, this yellow line would move depending in which direction, so you will obtain different predictions.
Because you also have to match the other abundances.
Yeah, so this
I
is.
don't think there is any change in the value of photon ratio can help you without breaking away a lot of other things.
I agree.
So I don't think this is a solution.
No, I don't think it's a solution. Okay, it's an hypothesis. Maybe I shouldn't.
She was setting it up as a straw man. She was going to knock it down very quickly.
All right.
She was on your page.
But it's a different possible solutions. I think this is not a solution.
I agree. I shouldn't have taken the word solution. Hypothesis would be more accurate.
It was a
So,
straw man.
but that's good to have an attentive audience. So different possible hypotheses. So this is an hypothesis, but clearly this will not work because you will have different abundances for nuclei that are well predicted, like deuterium and alpha particles.
But I think to solve that, you should have, the figure you had started below alphas and deuterium. And if you had that on that figure, then
Yeah, it would have
it
solved the
would have been
conflict.
obvious.
Yeah.
She truncated, yeah. The
Yeah, I
alpha-
know, but I know the figure.
Yeah, yes, we all know the figure.
So the second hypothesis is that there are some uncertainties in measuring the Big Bang nucleosynthesis abundances. And this hypothesis is basically that measuring the abundances in low metallicity stars might not be, the abundances in low metallicity stars might not correspond directly to the Big Bang nucleosynthesis abundances. But so anyway, a problem that we have in this lithium puzzle, let's say, is that you can see that you have very large uncertainties for example, the lithium-6 isotopes. So you have the Big Bang nucleosynthesis theory predicts abundances with that are very spread, let's say, or very broad. And this main part of the uncertainties come from the uncertainties on the nuclear reaction rate. And in this case, for lithium-6, the nuclear reaction that leads to this formation is the alpha D capture that fuse to form a lithium-6. So if we want to improve this prediction, we need to reduce the uncertainty in the description of this, in the prediction of this nuclear reaction rate.
Well, can I make a comment?
Mhm.
So this is a little informal. So you showed your cell phone, and it was my understanding that almost all the lithium beryllium boron on Earth was due to spallation reactions on mostly carbon and oxygen,
Mhm.
and that the Big Bang contribution to your cell phone is almost zero.
So it's funny when we
Is that
studied your
correct?
question, I thought that you were going to say like most of the lithium ions are lithium-7, which is true.
No. No, you get most, well, yes, but most of the lithium period, as well as beryllium and boron. So most of the lithium,
Mhm.
like the beryllium and boron, that we have, that are in your cell phone,
Comes from palliation.
comes from breakup reactions of usually protons on carbon and oxygen. And so I think that's the story as I understood it.
Mhm.
And that that's why you look at old stars, low metallicity stars, to try to get a Big Bang abundance, because you ain't going to get it from digging up stuff on the Earth, because that is been enriched by breakup.
Yeah, so I agree with you that the goal of showing the smartphone was more to make a hook than really saying that the lithium that you have in your smartphone was directly coming from that. But yeah, you're right.
Okay, so,
That's a fair comment.
sorry.
No problem. So when you want to know nuclear reaction rates accurately, what an experimentalist could think is, let's go measure it in the lab. So if you want to measure it in the lab, you could send a deuterium on an alpha particle and measure how much lithium-6 you produce with the the photon emitting. The problem is that you're interested in this reaction at very low energies, and the alpha particle and the deuterium are both charged, and so they repulse each other. And so you ended up having very low reaction probability, so very low cross-section. So this can be seen here, where you have the cross-section of this process that's going to depend on a negative exponential, which has the Sommerfeld impact, the Sommerfeld parameter here, depending directly on the charge of the deuterium and the alpha. So what is usually represented for this reaction is the S factor here. And you can see the S factor for different experiments, depending on the energy between the alpha and the deuterium. So as I just said, we are interested in very low energies because these are the ones that are relevant for the Big Bang nucleosynthesis. They are here in purple. And you can see that when you go to lower and lower energies, you have at some points no data at all. So you cannot cover the whole energy range of the Big Bang nucleosynthesis, but also the error bars become larger. So the reason is just because you have less constant statistics.
Yeah, no, I want to ask these questions first. Could you tell us about the green, which it's like
the green, okay, actually. So the green here, I'm going to discuss a bit more later. So the green is a peak due to a resonance in the lithium-6 spectrum. So I'm going to speak a bit more about it. So it's a 3+ resonance that you can see here. And the goal of this experiment, which was done in the 80s, was to get, or early 90s, I forgot, was to get, to actually probe this this resonance, this 3+ resonance.
So is that lots of different measurements that are somehow making that smear? So lots of little squares or whatever symbols?
Here, it's triangles, but yeah, it's a lot of little triangles. So this is a log scale, so this is where you look squished. So you have different type of measurements. So I'm going to talk about direct and indirect measurements. So direct measurements is basically sending the deuterium or the alpha onto each other and measuring the lithium-6. So you have this red data which corresponds to the lunar data, the green measurement that corresponds to the 3+ resonance, and here you have this black data which there is also a resonance here that is clearly more spread, more broad, so that you cannot clearly see with on the data. But then you have this data set here in blue, which correspond to indirect measurements. This is the way it's called. The nomenclature can be debated, but the idea is that they measure the breakup of lithium-6 on a heavy target. So the lithium-6 is going to break up into an alpha and a deuterium. And the idea is that if your breakup is only due to the Coulomb interaction, you can see this process as a time inverse reaction of the alpha decapture. Except that this idea is great, but there are some also a nuclear breakup that can contribute. And so these data actually suffer from systematic errors due to the fact that the nuclear interaction also contribute to the breakup of lithium-6. So between these two data sets, the blue and the red one, clearly the red one has less systematic errors, while the blue can be less trusted, let's say. So since we don't have data about the whole range of energies of interest, this is where theory could guide us. So you want to have an accurate model to predict the S factor and region that experiment cannot go. And most of the theories, all of them, have been based on two-body models, where you see the deuterium as a structureless particle and the alpha as a structureless particle as well. So here you can see a prediction. So let's focus on the solid line. This is the total prediction. They plot also the E2. So the prediction due to the E2, the quadrupole electric transition, and the S factor due to the dipole electric transition here, E1. So in general, the two-body models does a fair job. I mean, they reproduce the data where they are, some data. So it seems pretty good, but there are some downsides.
So sorry, let me just understand. That's a direct E1 and E2 radiative capture.
Mm-hmm.
But the E1 is there, but the rest of the lines, the ones that are not just E1, they're E2 plus the resonance contribution.
So the resonance is populated by quadrupole transition, because you have a 1+ ground state, and the resonance is a 3+. So is
I
the
see. Okay, got it. So the E2 captures the resonance.
Yeah. so. But so there are some downsides to these two-body models. The first one is that you don't know the interaction between the deuterium and the alpha. So you have to use phenomenological prescription. So clearly, talking about predictive power can be a bit dangerous there. The second one is that usually these two-body models are not evaluating M1. The reason why is they assume often that it should be negligible due to the fact that if you're in a two-body model, you know that your ground state wave function and your scattering wave function are orthogonal, so they should cancel, and most of the M1 should be nil. I can comment on that more later if you want, but I guess I would have to go on the blackboard to make my point very clear. And usually these two-body model, they are doing some phenomenological prescription to the dipole electric transition. So if you are strictly in this idea, you cannot have a dipole since the center of mass between the deuterium and the alpha is equal to the center of charge. So you cannot have a dipole transition, but what theorists have done is that to try to simulate this dipole transition, they've replaced the mass in the model by the experimental mass, creating artificially a dipole transition. The problem is that there was a recent paper 3 years ago by Daniel Bain who showed that using such prescription, you don't reproduce the physical behavior of the S factor at low energies. So this motivates the use of microscopic prediction, because if you're in a microscopic view, you don't need to use a phenomenological prescription for the dipole transition, and you can evaluate M1 easily. And this clearly motivates the use to use ab initio methods to predict this reaction. So if you want a complete ab initio description for a reaction like alpha D captured at least to the formation of lithium-6, you need to have some structure information. And this is done by taking in the wave function some no-Gaussian model states. So these are states which are expressed in a harmonic oscillator basis. And this part of the wave function will produce a very well-bound state in narrow resonance, so everything that fits in a box, and is very efficient to describe the short-range physics. So when all the nucleons are close together.
Sorry. So the center of charge, the center of mass, would be right if the deuteron wasn't polarized, as in the Oppenheimer process, the ancient one, where it tends to go in neutron first.
Yeah, this is exactly the point, is that in the two-body model, you cannot have this polarization because you don't know the internal structure of the deuterium.
So you're going to take care of that.
Because I'm going ab initio, yeah. This is the motivation of going ab initio on this reaction. So
low energy you expected.
Yeah, so you have clearly the deuterium. I mean, the deuterium, even at low energy, you can polarize or break up. You need to have some pseudo states, let's say, of the deuterium in your calculation to describe this polarization. I will have to believe you on that. But so when you're interested in the alpha D capture that leads to the formation of lithium-6, you don't only want to have structure information, you also want to be able to describe the reaction process accurately. So in the wave function here, we use let's say enhanced basis, where we added some dynamical cluster description, where you will have the alpha and the deuterium, and you solve exactly the relative motion between these two nuclei. So this is really accurate to describe bound and scattering states and reactions, and really takes care of the long-range physics. So when the alpha and the deuterium are far apart. So that's great, you have a wave function, but now how your system is going to look like. So if you apply your many-body Hamiltonian to this wave function, you end up with a matrix equation. So I'm going to guide you to it, don't be afraid. So here you have the Hamiltonian matrix, where you have a part that is the no-Gaussian Hamiltonian matrix, which is basically computing the Hamiltonian starting from the no-Gaussian model part of the wave function. Here you have what you call an RGM part of the Hamiltonian, which is basically the Hamiltonian with the anti-symmetrizer compute between the dynamical cluster states. And you have some cross term that you often call form factors, but you can call it as you want, which basically correspond to the Hamiltonian applied to the Nucleosynthesis model state on the left and the dynamical cluster state on the right. And on the other side, you will have the energies of the Nucleosynthesis model states. You will have what you call the norm of the RGM part of the basis, which represents the norm between two dynamical cluster states, and you have again cluster. So at this point, the goal is really to get these coefficients C and gamma, which are the coefficient between the Nucleosynthesis model state and the RGM part of the basis. So the way to do that is to use R matrix theory, so microscopic R matrix theory. And the idea of this theory is, you know that you have a distance between the alpha and the deuterium. So this is the little r here. And you divide your space into regions. The first one would be the internal region. And in this region, you would have both the Coulomb interaction between your nucleons that will contribute, but also the nuclear interaction. So you're really in the situation when the alpha and the deuterium are close together, and both interactions are important. And then you define an external region where alpha and the deuteriums are too far apart, and so they only interact through the Coulomb interaction in this case. And the great way of dividing the space in these two regions is that in the external region, you actually know the asymptotical form of the wave function. So you just have to compute the system in this region and then make some matching here to be sure that you reproduce some physical properties of your wave function, like continuity and continuity of its derivative.
Is this sum, or is there like a drop off, an exponential?
So here you mean.
Yeah.
So if you're looking at a scattering state you just you have something like this, let's say. It goes like this. So then what you will do here is that you're going to compute exactly in the internal region, and it's going to be like this. And then you know that you have to make a matching here. So you have to take a scattering state that has a right phase shift, and then you make the matching and you're going to keep on doing this. And then you have the wave function over the whole space. So it's really separate the space between a region that you know the asymptotical form, you compute the internal one, and then you match them together. So that's great. So now we have a method, we have a wave function, we know what we need to solve, we know how to solve it, but then you need to choose how the nucleons are going to interact. So which kind of Hamiltonian do you want to choose? So something that is very common in ab initio methods for the last 10 years is to use chiral-EFT interactions. And the reason why, chiral-EFT field theory, the reason why is that these interactions are grounded on the low energy quantum chromodynamics, and they are systematically improvable expansion. So the great thing is that by adding more orders, you know that you add more physics. So you really have a systematical way of improving the calculation. And the way it is done is that the long-range pion physics is included explicitly. So this is what you can see here, for example, the pion exchange. And the parameters of this expansion are constrained with data to capture the short-range physics that is not included explicitly in your model. And this is going to be a short parenthesis for the ab initio people in the room, because I know that there are some. So the kind of force I've used in this work is the N3LO 2-nucleon force and the 3-nucleon force at N2LO. And I use a similarity renormalization group transformation of the Hamiltonian to pass on the convergence. So the parenthesis is over. So now you have your Hamiltonian, you have your method, you know how to solve it. And the heavy part, and something that I realized going to ab initio methods, is actually that you spend a lot of time studying convergence. And this can be very time consuming, but also computationally expensive. So this work was, I think, possible because I was at Livermore, where they don't like computer, let's say. So in this case, I reached convergence by putting a bunch of lithium 6 Nucleosynthesis model states, but also the deuterium ground states and pseudo states that model the polarization that you were talking about. So this is important to reach convergence. And you have to go to pretty high model space. So you have to allow a lot of quanta of excitation in your model. So let's look at what you obtain for the scattering part. So you want to get the structure of lithium 6 right, but also the scattering right. So here you look at elastic scattering cross-section, depending on the deuterium energy when it's impinging on an alpha particle. If you put only the two-nucleon force, and I have to say SRG transform with two-nucleon force, you can see that you don't reproduce this peak here. It is a 3 plus peak. And you don't reproduce the peak over here, that is a 2 plus peak, so another resonance. So these two peaks are two resonance peaks. When you include the three-nucleon force, so the one that is induced by the fact that you did this unitary transformation, and the chiral one, you obtain something that is in way better agreement. So the 3 plus, I was very lucky on that. We just no adjustment, we were on top of it. And the 2 plus is also very well reproduced. So,
how do you do on the spectrum of lithium-6 straight up?
what?
How do you do on the spectrum of lithium-6 straight up?
That's the next question. So you are able to do the scattering part, but what about the spectrum of lithium-6? So we had a similar thinking about it. So the lithium-6 spectrum, so here you can see the prediction on the left and the experimental spectrum. And you can see that the ordering of the states, so I'm looking at the low energy part of the spectrum. So here is the alpha D threshold. So this is the first 3 plus resonance and then the 2 plus resonance here. This is the ground state. So the ordering is right. The 3 plus resonance is right. It's really on top of it. But your ground state is overbound by 300 kV and the 2 plus is slightly overbound as well. So the thing is that 300 kV might not seem that much, but when you want to study the capture of an alpha and a deuterium to fuse together, you want to get the ground state properties right. So you want to be on top of the experimental data in this case. And this is where you actually have to leave a bit the ab initio ID behind to try to make an accurate evaluation. So, yeah.
How does the reaction
The alpha D1?
Yes.
So it doesn't depend because it's the long range part. So in general, it should be fine. So yeah, so this, if you want to have a, let's say, accurate evaluation of the S factor, you have to get the binding energy of lithium-6 correct. So this is where we use a phenomenological correction, where we play with the no-Coulomb model. We tweak the no-Coulomb model eigenvalues for the full no-Coulomb model with continuum to produce the experimental data. So this would be here the initial prediction. After tweaking this value to reproduce the experimental data, we obtain this spectrum. So by correcting phenomenologically, we have the right binding energy of all the states of interest here. So if you remember the Hamiltonian matrix that I showed in the beginning, you had 4 parts. So you have the Hamiltonian of the So you tweak the eigenvalues of the no-Coulomb model states. So you change this value for the full no-Coulomb model with continuum to reproduce the experimental data. But this value is not put as the experimental data because the model space is way larger than that. So actually you have to fit, right? It's like you have to.
Sorry, you're changing 2 things.
I changed the 1 plus energy and the 2 plus because this was the 2-1. But when you change the 1 plus, it's gonna only change the 1 plus channel. So the fit can be done separately for the 1 and the 2. So I'm changing the 2 eigenvalues of the no-Coulomb model.
Question from the Zoom.
Yes.
The experimental width of the 2 plus is still quite a bit larger than what is given by the calculation. Isn't that a problem?
So it's not ideal, but in this case, the Big Bang nucleosynthesis relevant energies are between 30 and 400 keV. So even the 3 plus resonance is above it. So
Okay.
not gonna influence the prediction that we want to make.
But it has a large width, so it trickles down quite a bit.
Yeah, but it's not gonna reach 400 keV because if I remove it, I can. It's you can play with the model spaces. If you remove it, you can see that it doesn't influence the low energies.
Okay.
So, okay, so we make this phenomenological correction, but then after doing that to reproduce the lithium-6 spectrum, you have to come back and say, okay, how did it change for my scattering observable? Am I still able, with this phenomenological correction, to reproduce the scattering observables? So here you have a comparison between the full ab initio that I showed you earlier. I removed the 2-nucleon force here, and the one using this pheno correction. And what you have, and not very surprisingly, is that you have produced better 2+ states because your shift is position. But also you have quite some change at low energy here. And this change at low energy are really due to the fact that you adjust the energy of the ground state of lithium-6, so this 1+ ground state. And so this is going to influence the scattering data at low energy. So that's great. So the spectrum and the elastic scattering part are well reproduced. So how does it look for the alpha decapture? So what I promised I was going to show. So you have the S factor as before, the relative energy between the alpha and the deuterium, the same experimental data that I showed before. So here you still have the 3+ very well reproduced, was not adjusted, very well reproduced by the ab initio calculation. And you have the full ab initio, so nothing adjusted by the dashed blue line. And you have the ab initio corrected, let's say, or evaluated by the solid red line. And as for the scattering observable, you can see that the main influence of this correction is at low energy. And again, this is due to the binding energy of lithium-6 that is better reproduced, and around the 2+ resonance here that is not very clearly seen from the experimental data, but shifting its position is going to shift the move is going to influence the S factor these energies. So the way to think about this difference that we have here between the no partial model full ab initio and the one corrected is that the initial ab initio prediction were predicting overbinding, and so it's harder for the alpha and the deuterium to fuse together. They will have less cross section. So, okay, we have the full ab initio calculation, but now an important question to ask is, was the way that we were doing computing dipole and quadrupole electric transition and dipole magnetic transition was correct? So, which electromagnetic transition drive this reaction? And so here you can see the S factor decomposed between all these components. So the full calculation is the solid red line. The quadrupole electric transition is this dashed black line. The dipole magnetic is the dotted green line. And the dipole electric is the dashed dotted blue line. And as for the phenomenological model, we see that quadrupole electric transition dominate the capture. And electric operator are actually very sensitive to, let's say, the long-range part of the bond state wave function, so to the asymptotics. So it's really important to have the asymptotic right. So in this case, the asymptotic of a bond state wave function is given by what we call an asymptotic normalization constant that gives you the magnitude of the exponential decay of the wave function. And I've compared what we obtain in this case with a previous analysis done almost in 2000. Where they analyzed the phase shift between the lithium-6 and the alpha, and they extracted A and C. So for the bond state of lithium-6, you have two partial waves, a S and a D wave. For the S wave, you obtain an ANC that is larger than what they extracted from the analysis. For the D wave, we have something that is agreeing well. And interestingly, the ratio between D and S is very similar. And why is it interesting to have the ratio to be very similar is because this ratio is actually what is going to influence other reaction observable like transfer cross-section. So if you were to populate a lithium-6 ground state. So in general, the ANC that we found starting from nucleons degrees of freedom are pretty consistent with what was in the literature. The other interesting part is that we obtain a negligible ion transition, so we don't verify this phenomenological prescription that was used in the past. So really starting from no phenomenological prescription by replacing by the experimental mass, we obtain something phenomenological, negligible. And finally, the M1 transition here are important. And this is something that well, it was not seen before. So that's something that was kind of surprising. And when something is surprising, and a good reflex is to actually look at other observable that are sensitive to this M1 transition. So if you look, for example, at the dipole magnetic moment of lithium-6, so this is the one we predicted, so 0.84, and the experimental value is not too far from that. So this kind of confirmed that our prediction is realistic. But then the second thing, and I presented these results in November in Brussels, and some specialists of two-body models and predicting astrophysical rays were asking me the question, why this M1 looks like this? This is very strange. And I didn't know, so I actually spent a few months looking for this answer. And the first, let's say, way that I looked at was, does the SRG transformation of my operator is going to influence the shape? And so if you SRG your operator, so here only M1 because you know that E1 and E2 are long-range operators, so the SRG transformation will most likely not impact them. So if you look at the SRG transformation of the M1, you have an influence, but negligible, you still have this weird shape and it does not influence the total S factor. So on that, it was good. So it took some time to check that. But then I did some check by removing some transition to try to understand what was happening. And what I noticed is that basically this weird shape arises from the fact that we account for the deuterium and the lithium-6 structure. So kind of arise from interferences between M1 transition within deuterium and lithium-6 states. And I was happy to see that there is another paper from 2001 using continuum technique. But actually, if you look, I saw this paper before, but I never pay attention at that until I came back to it. They have this M1S, so this is the M1 transition in the S wave. And if you look at the shape, they also obtain some kind of dip. So it goes down and then it goes up. And so this really confirmed the fact that this weird shape of observed in enhancement at low energy is really due to the fact that you include the internal structure of the deuterium and the alpha. So I was happy with this answer because I knew why the shape was weird. And so that's kind of concluding this analysis for the alpha D capture. So really the motivation is to reduce the uncertainty of the rate that is useful to predict the abundances of lithium-6, so the Big Bang nucleosynthesis abundances. So in this case, it's important to go microscopic to remove some of the assumptions made on the electromagnetic transition. And I've shown you that the ablation method here is actually to reproduce elastic scattering, ANCs and moments, as well as the S factor. And we were able to provide the first ab initio prediction using 2-nucleon and 3-nucleon chiral forces. So looking to the future, we need to propagate our evaluation of Big Bang nucleosynthesis code, or at least evaluate the rate. So it's something that I still have to do in the next weeks. And finally, it would be nice to actually have an idea or control of what is the uncertainty of our prediction depending on the chiral force that we put in this model, final prediction. And with this, thank you for your attention.
You teased at the idea of why that M1 transition wasn't evaluated before. It seems like it's now quite important. The ranges that are necessary. Like, so what really is going on there?
So a lot of people are avoiding this problem.
Yeah.
So the M1 transition would be basically an M1 operator, let's say, we have a scattering state on the right and a bound state on the left. This M1 operator can be written as the sum of an orbital angular momentum operator and a spin operator. And this, we can write it as being, just write it as a total angular momentum. And then the rest depending on the spin. People are saying maybe I shouldn't have taken the one. So if you focus on the first part, so you know by Wigner-Heckart that you will have, I'm not going to put the coefficient, but you have a curved Coulomb basically, and then you can write it for a while like this. And since these two are solutions of the same Hamiltonian, what's going to happen is that you're going to have the projection here of, I don't know if you can here, and then you end up just with the overlap between the bound state and your scattering state. And since they are solutions of the same Hamiltonian, this overlap is 0. So basically the argument is, you know that this is going to be 0, and this small part should be, this part should be small, but nobody's computing that. What we see here, so we still verify this idea, but is that this spin part is not negligible, and this is what is creating these important M1 transitions.
Thank you.
I can ask more questions if it's tolerated. Okay, so the M1's important, but you're still going to have a dramatic underprediction from Big Bang models of what is the astrophysicists' claim. You should, and once you double back and see that it's true, that the lithium-6 decomposition, which is tough, is valid. So the blue points there are from the lead experiment.
Yeah.
So hopefully they know they more or less wasted their time. But I want to understand what they did. Is this higher angular momentum in because this is a in the Coulomb, you have virtual photon field from the lead. And so what are they doing
so
to give you extra cross section? What are you're not calculating it, okay? But there's a reaction there in a virtual photon field. What is there that is not in your calculation?
So
what's going on there to create lithium-6?
So
if it is in fact creating lithium-6, maybe it's breaking up the deuteron. I don't know. But what's there that's not? It's not a Big Bang, probably, of course.
So the thing is that, so as you said, there is a photon field,
Yes.
but you have a nuclear field between the lead-208 and the lithium-6. And the way they analyze the experiments, they're actually neglecting this nuclear field.
So you think it's not in the virtual photon field?
So
you think it's nuclear?
So I think there is nuclear interferences, and there are many reaction theorists, and so Phenomenological also showed up at this point, at some point, but that actually said when you want to do that, so infer capture from a breakup on heavy targets, you need to account for the nuclear interaction and its interference with the Coulomb interaction. So probably also E2, but so the cross section, I'm guessing, I don't have it in mind, but I'm guessing should look like a peak, something like this, because it's a heavy target. So if you put only Coulomb, so this would be the cross section of the breakup, depending on the energy between the alpha and the beta. So I really have the beryllium-11 in mind, but I'm guessing that this shouldn't have two different cross sections. So this would be the experimental cross section. Let's say if you put only Coulomb, you can have a situation where you will have something like this with one model, and if you put only nuclear, you will have something like this. So this would be the nuclear part of the breakup. This would be the Coulomb part of the breakup, and you cannot sum them to obtain the total cross section. You have some interferences between these two breakups, let's say, and the fact that they only include Coulomb in their analysis. So because when the fact that they only include Coulomb in their analysis make them having some systematic error in the radiative capture that they extract. So basically, they analyze it like they think that the lithium-6 is not interacting with the nuclear interaction with
I
light.
understand what you're saying there. I'm just trying to understand why it's always north, why it's always more.
It's not always more.
Well, here it is.
Here it is because it's one system at one energy. But if you look at other kinematics or the nuclei or the targets, it's changing. There are some people that do some systematic analysis, and this is what is also annoying. Is it can go in both directions. The conclusion is that if you want to extract, capture information from breakup experiment, you need to be sure that the reaction model that you're using treats consistently both the nuclear and the Coulomb interaction. And
So they went to lead to try to, and at these energies, the deeply sub-area,
yeah,
right? So the distance of closest approach is
so
10 times the nuclear size.
So I believe that this reaction, and this is going to be from the top of my head, but I
no,
believe this reaction was measured at 30 MeV. So they send the lithium-6 30 MeV per nucleon.
Per nucleon?
I have to check. But it's not exactly this energy. The thing is that from, it doesn't change really the conclusion. From the analysis that you get the internal structure. So you have the cross-section, and what you're going to do is to map. So you have the cross-sections, and you find the description of the alpha deuterium system that match this cross-section. Basically, that's the idea. And from this, you can compute the capture. And there's very few body view, but this is basically what is done. Is that they use the breakup to constrain the structure of lithium-6, both the scattering, because with breakup you explore the scattering states and the, let's say, ground state part. And with that, they can compute after the capture. The problem is that if your breakup is poorly reproduced, you will have a shift in the structure of your lithium-6, both scattering and bound states, and then also in your capture section.
Do you happen to remember who did the heavy ion breakup?
So the first experiment was, I think, in the 90s, but I'm going to come back to the figure, where, so the blue data, no, 80s. Yeah, it's Kinner, okay, Kinner 81. But the thing is that what I want to show was not this, because it's a detail that I didn't want to influence here, but basically the MAC evaluation is based on the Skinner 81, but 10 years ago, Francis Samash, we did the analysis. He wanted to do the lithium-6 breakup, and he concluded like we are not able to separate Coulomb and nuclear interferences. We are going to extract a new upper limit, and what was done in the past was not good. Basically, that was the conclusion of the paper of 2010-11. And so what they did, they were way more careful. They didn't produce a data set like the previous one. They just gave a new upper limit. So there is different way of trying to remove these Coulomb nuclear interferences. Some of the experimentalists are selecting in angle. So if you go to very forward angle, you have more Coulomb.
Here's a group at Argonne in Rochester who working on this. So let's say we know it's not that eta is wrong, the area and the photon ratio. We know it's and let's say okay, so you've solved the new. Let's say you do your work is ironclad and it's extrapolated to low energy and doesn't solve the problem.
Mm-hmm.
So it's not that. And let's say the astrophysicist looking at those old low metallicity stars did their job right, and that is an accurate lithium-6 abundance in these things.
Mm-hmm.
I come back to my first comment that was in your cell phone. Most of the lithium is not due to Big Bang.
Yeah, it's other reactions.
It's due to breakup of something heavier that jumped over the mass 5-8 problem,
Mm-hmm.
went heavier, and then broke up to come back. So how do we know? Isn't a reasonable conclusion that what we're looking at in these old stars is a lot more like us or our neighborhood? Right, but
right? And that's the
Yeah, but this plateau seems, from what I read, I'm not an astrophysicist, but
So you didn't say anything about lithium 7, but
No, this is.
you have eight the problem. So yeah, it's a,
Yeah, you also have a problem here.
yeah, but they are. Well, it's open.
So
But
the,
in both cases, the measurements are getting more. Sorry, we have reduction of lithium 7. Sorry.
Yeah.
The data in lithium 7 is low. So that's the argument against what I was just saying.
Yeah. So unless you have some lithium 7 that goes on to the fixed.
yeah.
That's
But that's the other hypothesis, is that there are some other reactions outside this network that maybe contribute and shift things apart. But which one is not clear, but I think, so it seems that, let's say, you have different fields involved in this kind of prediction. But the role of nucleosynthesis is to reduce the uncertainty. The role of an astrophysicist is to actually verify that the measurement makes sense.
The problem with the lithium 7 being 6 is that the T alpha threshold is much lower than the lithium 6N threshold. So if you excite lithium 7, you're going to get T alpha, not lithium 6N. Well, I'm overwhelming. That's not categoric, but it's overwhelmingly that way. You don't go with the right thought.
Thank you.